and actually those are the only two possibilities. So one of those is the right number. If you remember, okay, so that's based on the 2. The 2 tells me it's going to rise as we go from the left to the right. And then the second value, the 1, tells me where it's going to cross the y-axis. And so over here, wow, my alignment's off pretty poorly, pretty much. Well, that would be the number 1 anyways, is what it's telling me. So that's sort of what we saw there. If the value out front here or here is negative, essentially the original graph is flipped. So with a straight line, if we have a negative value in front, it's going to be decreasing as we go left to right. And with the parabolas, assumedly you notice that the rest of all of the second power things are parabolas. If it's a negative, our parabola is going to look something like this. If the number up front is positive, it's going to look like something like this. And just to clear up one of the first questions, the leading coefficient, the idea of leading coefficient, is the number in front of the biggest term. Sorry, biggest, I guess. So in the case of the straight lines, we have an x term, and we're looking for the number in front of the x term. When we have an x squared term, we're looking for the number in front of the x squared term. Today we'll be looking at cubics, so x cubes and x to the fourths. If there's an x cubed, then you're looking for the number in front of it. If there's an x to the fourth, you're looking for the number in front of it. So it's always the biggest power. We're looking for the number in front, which takes me to a second question, I guess. And it was just the idea of degree. And the degree of the polynomial is just the exponent of, again, that biggest term. So up here we have a degree 2 polynomial. Here we have a degree 1 polynomial because x to the exponent 1 is the biggest exponent on one of our x's. Hopefully those two terms are cleared up. I'll put some sort of slightly better definition maybe in the note, but that's the idea there. And then basically this is an observation table. So sort of going across here, domain and range. When we looked at the first one, the graph, sort of sketch it super quickly here, looked something like this. So domain, I'm just going to move those over. All right, that works. Domain is all the x values that are covered by our graph. Well, in this case, and this is sort of the syntax, if you remember, x belongs to the real number system. So x can be anything at all. For our purposes, this is all I need to see. If you do take math next year at college or university or something, you might end up with having to write a little bit fancier notation, but this explains to me that you understand the concept. All the x values are possible. If you don't remember how to write that way, write down domain, x can be any number, and I'll be fine with that. Our range in this case, if we look at the green line, it could extend down forever, up forever, and so same sort of idea. The range is that y can be any real number. Now the other two things we've discussed, the degree is 1, because it's x technically to the exponent 1. The leading coefficient is 2, so the number in front of the highest degree. And then the last thing here, n behaviors, was kind of the third question that I was given. What the n behaviors that we're asking about is what happens on the ends of the graph. So over here, This is implying that the values continue to rise as we continue to go to the right. So essentially, as x heads out towards infinity, y also heads towards infinity. So x gets bigger and bigger and bigger, y gets bigger and bigger and bigger. If I look at the next one, or should the other part here, I didn't mean to write that. As x heads out to the left, and it gets to be negative numbers, negative 1,000, negative 10,000, negative 10 million, negative 10 billion, the y values also head towards that same set of numbers, negative 10 million, negative 10 billion, and so on. So that's that's how we write the end behaviors. Again, what it's reading is that as x gets really, really big in the first case, y gets really, really big as well. In this case, as x gets big negatively, or I guess you could think of it as small, but as x heads towards negative, really large numbers, y also heads towards those same really large numbers. I'll do one more down a little bit here, number 5 maybe, just to save the overlap. Without getting into too much detail, the graph essentially looks something like this. Let me factor that out. Wait, sorry, x comes out. I'm left with 1. So it actually looks like something like this. And then same basic ideas. If I go through, I've lost what I've actually been asked to find. Domain and range. Well, this graph continues on forever this direction. And if I did draw it out, it would eventually head out to the point where x will be any real number. It's going up much quicker than it's going out, but still I can get further and further out eventually. And I'll kind of discuss that a little bit more in just a second. Range, same idea. Basically, if we look at this one, and I would actually have to go back to the other side of the graph to get the actual number here. But when I look at the y values, there is a minimum value right down here. Whatever that number happens to be, that's kind of my key point. And so maybe I'll flip back and kind of quickly scan them, see if we can pick up the right answer here. So there's only 2 possibilities. And as I said, this is the one here. Can't even really read it very well, but it looks like, oh, what a surprise, -6. And so coming back to this side, essentially, the -6 value is going to be the lowest possible value on the graph. So my y values will all be greater than or equal to -6. And that kind of makes sense if we just plug numbers in here. When I put a 0 in, I get 0 plus 0 minus 6. When I plug a 1 in, I get 1 plus 1 minus 6. Actually, I'm lying to you. It's going to be slightly below that, but I can't see very well from the graph. So just to get an idea, if you sketched it, you would have got a little bit slightly better answer for this. But that's approximately what it is. Finishing up, degree, same sort of idea. The degree is the exponent here, so hopefully that's clear now. It's just a 2. Leading coefficient is the number in front of that term. It's 1x squared. And then the end behaviors, again, probably really the important thing here, is what goes on as x goes one direction and the other. As x goes out towards infinity or positive infinity, y gets really, really, really big. As x heads out towards negative infinity, so as x gets to be really large negative numbers, again, looking at the graph, the y values are actually heading up towards positive infinity because they're getting bigger and bigger here, even as x gets to be small. Now, the one key is one thing I want to always encourage students to do is don't try to memorize these sorts of things. This isn't something that you need to know. When I have an exponent of 2 and I've got such and such, then I will get this situation, especially with an n behaviors. What I'm going to do is, if I'm looking at a specific question, maybe number 7 down here, if I'm interested in the n behaviors, even if I don't see the graph, all I'm really doing is thinking through this mathematically. So if I'm starting with something that looks like this, and you ask me what are the n behaviors, what I'm interested in is as x gets, again, really close to negative infinity, gets really, really big negative numbers in there, what happens? Well, all I have to do is sort of think about that a little bit. If I put a number like negative 1 million in here. Now again, I wouldn't necessarily write this out, but just for the purpose of talking it through, what I get is this. When I punch, if I did punch this into a calculator, this number in the first part is absolutely huge compared to this number. This is 1,000,000 times 1,000,000, and this is 5 million. So this is 1,000,000 times bigger, essentially, or very close to it. Which means that as far as determining the end behaviors, all of this stuff is irrelevant. So all I need to do is look at, sorry, I said negative, so I guess I would be putting in negatives there. But all I have to do is look at what happens in this one section of the graph, in that first term. I have negative 1 million squared. I'm going to get a positive value in the brackets. Because there's a negative number out front, I won't write that way. Because there's a negative number out front, the positive value in the brackets overall is going to be negative. And so what that tells me is, as x becomes really, really large negatively, y also becomes negative. Same argument then, if I'm thinking about x going towards positive numbers. Now this is positive 1,000,000, this is positive 1,000,000, but again, all of this stuff is still completely irrelevant. Positive 1,000,000 squared is a really, really big positive number. Oh yeah, but there's a negative sign out in front. And so y would also approach negative in that case. Okay, so hopefully that's not too bad. Again, not a bunch of rules in math. I don't know if I've said this to you guys specifically, but I try to stress it with all classes. Math is not about learning rules. There are sometimes rules you do need to learn, but really it's about thinking about a situation mathematically. It's asking me what happens when I have some really big numbers. Well, put some really big numbers in mentally if you can. If not, then you can fire it off on a calculator and get an idea what's going on. So I guess I don't have to go through these now because they are essentially the same question. Domain, range, degree, just having you kind of practice a little bit on your own. And then today's work will look pretty similar. So this is the first handout, and it sort of describes the end behavior. It shows you sort of the number of intercepts. Number of intercepts is the one new thing. Number of x-intercepts specifically is how many times do I cross this line, the x-axis. So on this one, obviously, I can see I'm crossing it once. And this one, I'm crossing it once. Your job will be to sort of go through a few of these and determine, is there some sort of a patterning there that we see? And if there is, sort of what is it? So basically, I'm giving you, the first two are sort of given, and then I'm asking you to do 2 per graph, essentially. There's not, it doesn't take up a lot of room in any of these. Essentially, this is going to be, what is the leading coefficient? 1 here, negative 1 here. So you can kind of do a split screen, if you will. I didn't split it for you. Number of x-intercepts. Oh, okay, well, until I actually see the graph, I'm not going to know these answers. And then what happens is, again, once I see the graph, I can fill in the other 2 sections as well. What I would suggest here is basically, maybe work in 2 different colors, if only for the graph. But if you do happen to have a two different colors or a pen and a pencil. If I did something like this, then I could draw this graph and this graph and know which one represents the top equation, which one represents the bottom. So just for space, I kind of put everything on one page. I didn't see any reason for you to print off 3 or 4 pages to do that activity. And then basically just a summary of that. There'll be a similar one for the quartic functions, which are the fourth powers. What do you notice about the leading coefficients of the polynomials? I'll have to edit that a bit. It's not the actual final version. But basically it just says, what do you notice about the coefficients? How do they affect the graphs? What's true about the end behaviors of the polynomials? So just a general summary. What did you notice? I noticed that when blah, 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 this seemed to happen. I noticed that, and so on and so forth. Okay, so I'm going to stop there. It's a little longer than I meant to go, but hopefully it clears up any issues that we had. As always, I encourage you to sort of get on and start working during class time instead of maybe at night as much, and then you can sort of fire questions my way. I'll say usually I can answer emails at night. I didn't last night. I know somebody sent one, and they sent it because I told them to send it when the pages aren't working, and it just happened that my phone was dead last night. So, new battery actually today. I just charged it overnight, and hopefully that won't happen again. But if you're working on it during the daytime, like I said, I'm around most of the time. Period C is the one period where sometimes I'm doing something else. But the rest of the time I'm on the machine. It just whether or not I'm paying attention to the window. So an email, a page, and a little patience, and you should be able to get a hold of me pretty quickly. So I'm going to stop there. This is one of the longer videos. Didn't intend it to be, but that's okay. Hopefully it covers what we need to cover.